So welcome once again to the third part of the slide videos looking at the Texas Instrument TI-30Xa calculator and its application to the RSGB Advanced Certificate Examination. Now in the first part of the series on this calculator, we focused exclusively on the calculator and its buttons. In the second part, we covered the first part of the formula sheet that you get given in the exam, which you can see here on the screen. And we covered the equations up to and including xc equals 1 over 2 pi fc, the reactance of a capacitor. As I've said, I think a couple of times through the videos, don't worry too much if the science or the engineering behind the formula don't make sense. It doesn't make sense because in these 3 videos we're just really looking at how to use the calculator, and the spin-off is that yes, we get to apply them to the equations, and I do try and set a little bit of background to the equations. So you can see the page here. We've got as far as the blue highlighted equation, and we've got the remainder of the page to go. You can see here that the amount of equations is significantly more than you had to take on board for the foundation or indeed the intermediate. So this is really quite a step up, and what you're doing here is quite complicated, and I've had a look at the electronics exam syllabus, and I would say that overall it seems the A-level electronics exam syllabus, I would say overall it looks of a comparable level. So it's not trivial, but I guess you knew that when you started this course. Right, so today we're going to go on and have a look at the remaining equations. I hope to go through them, at least most of them, before the end of this video. And I'm taking the equation sheet here from the syllabus, which you should all have downloaded by now from the RSGB site. Remember, the syllabus will be changing next year, so it'd be nice to get through this exam before the changes take place. So here we have it then, the Advanced Radio Communication Examination schedule as well. Now, a lot of these formulae fall into section 3, and you can see that section 3 here accounts for only 12 marks out of the total. I think if you look at the licensing conditions, it accounts for 10, section 3 12, and transmitters and receivers, some of them fall into transmitters and receivers to be fair, 13, feeders, some of them fall into that as well, 5, propagation, I don't think there are any calculations in propagation. EMC, yes, there is a calculation or two. Procedures and practices, I don't believe so. Safety, I don't believe so. And measurements, yes. So we don't want to over-focus on the calculator use. However, it is an important part. So there are a total of 62 questions, and I would say probably of the order of 15 or some of them will require some calculations. So, while we don't want to over-focus on it to the exclusion of everything else, we do need to get this calculator on board. So without any further ado, let's push on with the remaining equations and have a little tour through those. So the first of the remaining equations we're going to look at, F equals 1 over 2 pi root LC. Now this equation relates to the resonant frequency of either a series or parallel tuned circuit. If you recall the two requirements, well, the requirement for a tuned circuit is for it to have a capacitor and an inductor. And there you've got a series tuned circuit with a C and an L, capacitor and an inductor. You could also have a parallel tuned circuit looking like that with the two components in parallel. And the formula below that you can see on your screen relates to both of them. So let's look at it from the point of view of the calculator once again. You might remember which one is an acceptor circuit and which one is a rejector circuit. In other words, which one is low impedance at resonance and which one is high impedance at resonance. Have a look at the video on tuned circuits if you don't remember that. I'll give you a clue. I'll tell you what it is. It's the acceptor circuit is the series tuned circuit, and that's low impedance at resonance, and the parallel tuned circuit is the rejector circuit, and that is high impedance due to the circulating currents at resonance. So let's put some values on C and L. Let's put in 0.1 microfarads for C, and let's put in 200 millihenries for L. So we go to the calculator, switch it on, and it's in already seems to be in engineering mode. I'll switch it off, so we start off, then switch it on and off, and we start off as we would if it had been switched off. It had obviously just gone to sleep. So I think I'll put it into engineering mode, so second engineering, and I can see the enunciator and the 2 zeros there. So let's work out L times C first. So if I write the equation then on the blackboard here, right, F is equal to 1 over 2 pi root LC. Now when you're attacking these equations with the calculator, sort out the most complex bits first. And the most complex bit is getting L times C and taking the root of it. So let's do that first. We'll start at the bottom of the equation. Don't necessarily just start at the top and then do the bottom. You can do, but you'll end up using brackets quite a bit. So it's easier just to pick the most complex part first. So let's pick LC. So we said L is 200 millihenries. Okay, so I'm putting in 200. EE 3, change sign. That's my L, 200 millihenries. Times C 0.1 EE 6, change sign. So that's my LC, well that's my C, and to evaluate L times C I press the equal sign. Equals. Now I can take the root of that, so I've got the square root button up here. There's the root of it. I'm now going to multiply it by 2 pi. So times 2 times pi equals. So now I've evaluated the bottom of this fraction here, and it's 888 point something. 0.57. And that's in the X register of my display, but I need 1 over that. So now I'm going to press 1 over X. Okay, and the answer comes up on the screen. It comes up as 1.125 times 10 to the 3. And of course, because it's F, the unit is hertz. Now 1.125 times 10 to is 1.125 kilohertz. 1.125 kilohertz. And you should be recognizing 10 to the 3 as being kilo. It should be now second nature, or it certainly needs to be second nature for you. If we wanted to write it down in hertz, we would use the decimal point hopping technique, and we would write it down as 1.125, and we would hop 3 places to the right. 1, 2, 3, and then put a decimal point there, put a 0 after it to make it quite clear, is 1125.0 hertz. In other words, just over 1,000 hertz, just over 1 kilohertz. If we wanted to do that on the calculator, we can use the second function, float button, and now you can see on the display it says 1125.3. I ignored the decimal places before, so that's why there's a discrepancy there, but nothing has actually gone wrong, apart from the fact that that I ignored those remaining decimal places. So if I want to go back and see it in kilohertz, I press second function, engineering. So by going between second function float and second function engineering, I can see the result either in the base units or with the appropriate engineering multiplier, which will be a multiple of 3 and will correspond to one of those prefixes that we know and love. Okay, that's pretty much the working out what the resonant frequency is of a tuned circuit. Again, don't worry too much about this if you don't understand what's happening. That's okay, it's entirely okay, because we'll be sorting that out in videos and in class. So let's have a look at this one here. Now what have we got here? We've got T equals 1 over F. That was in the intermediate course. That was part of the syllabus for the intermediate course. And I don't believe you had a sheet with that written on. You had to remember it for the intermediate course. So the advanced course is easier in this respect, in as much as they've written it down for you. If you recall there, if you had a waveform and you recall that it was sinusoidal, a sine wave, a very good sine wave, but there you go, and that indicates one cycle. And the vertical axis, that could be voltage or it could be current. But along here, it will always be time, or small t for time. Now, a period, one period, is one cycle, and that is capital T. The time taken in seconds for one cycle. And the frequency is in hertz. Now what they'll be asking you here is they'll either give you the period or they'll give you the frequency, and you need to find out the corresponding value. So useful here to be able to change the subject of the formula. T equals 1 over f. If I multiply both sides by f, I will get TF equals 1. And if I divide both sides now by t, I will get f is equal to 1 over t. Again, if you're struggling with that, don't worry. We'll sort it out in class. We'll be doing the changing of for these sort of 3 variable type equations. We'll practice a few of these and you'll soon get the hang of it. So these are the 2 that we'll be using for the calculator. The one they give you on the formula sheet, which I've labelled 1, and this one here, which looks like a capacitor, so I'm going to make that a bit longer, which I've labelled 2. So let's say, looking at 1, we are told that t, the period of one cycle, is equal to 1.5 microseconds. And we're asked to find out what is the frequency. Okay, well, sorry, we'll be using this one first of all because we're finding the frequency. So f equals 1 over t. This is a very simple one to do on the calculator. We just clear the calculator, put it into engineering notation. It's already there. We will say 1.5 E6 change sign. So there I've got in there 1.5 microseconds in engineering notation in the display. And that's in X. So that has filled in that bit here. So I simply press 1 over X. Okay, and that will give me the frequency. And it says there 666 times 10 to the 3. Or 666 kilohertz. We'll do another one now. We'll say, if I can just get an area of screen, this new calculation here, we'll say there's a frequency of 100 and 5 megahertz. What does t equal? Going to the calculator, we press clear. 105 EE6 megahertz. That's in the display, the X display. We need 1 over that. We press the 1 over X button, and we've got 9.52 times 10 to the minus 9. Oops, I'm writing it down in the wrong place here. Sorry about that. 9.52 times 10 to the minus 9 seconds. In other words, 9.5 nanoseconds. Minus 9 being nano. Now we go to the second function, float. It'll give us the wrong answer because it'll do its best. It's rounded it up to 1, but basically there are not enough digits to show the precision that we need in float. This is why, generally speaking, you want to have the thing displayed in engineering notation. Good. Right, we'll move on to the next equation. And here we have tau equals CR. Now, I've done an extensive video on time constants. I believe there is a little bit of confusion as to whether a t is used sometimes or tau is used. And I'm trying to think, I think it may be that in the book they've used a t, or maybe in the text in the syllabus they've used a t. I think it's just a font thing. They didn't have a tau or something like that, or maybe a small error. But tau is normally the symbol used, but if they print a t or something like that, that's okay. It's sort of acceptable. So we'll stick with tau for the time being. Now, the time constant here is looking at the amount of time taken for a capacitor to discharge. So T is going to be in seconds, C is going to be in farads, and R is going to be in ohms. So let's have a look at a capacitor discharging through a resistor. Or let's say charging. It's charging or discharging. Let's have a look at a capacitor charging through a resistor. There's a switch there and a battery. And if we measure the voltage across the capacitor, and we look at the time taken after the switch is closed, we'll get a curve, and we can interpret this curve in terms of time constants. As I say, there's a video on this, so I'm not going to delve into this too much, but I'm just going to put some values in so that we can put the equation through the calculator. So here we go. Let's say we have 10 picofarads and 1 kilo ohm. Let's put that into the calculator. Again, we're already in engineering notation. So pico, remember, is 10 to the minus 12. So I'll put in 10 EE12, change sign. So I've got 10 to the minus 12 in there. Times 1 kilo ohm, that's 1 EE3 equals. So that's simply it. I've got 10, I think. Sometimes I've made a few mistakes. I think in the first or maybe the second video, I'm looking at the display from an oblique angle because I've got a little webcam above it, and sometimes I've missed the decimal point, and so there's a mistake or two which I'm sure you'll spot in the second of the videos, and I may do that again. So if you get a result that you don't think is correct, trust yourself, you're probably right. So this says 10 here, CR, C times R, is equal to 10 times 10 to the minus 9, and because it's in seconds, time constant, I'll put tau is equal to CR equals 10 to the minus 9 seconds, and that means 10 nanoseconds. So fairly easy to work out CR, but you will normally have fairly small values of capacitance in the CR ones, so make sure you enter it in correctly. Moving off to I think we're in the third column already. Yes, moving down and on to the next row. We have an equation there, or two equations, to do with Q, and there is a dedicated video on Q on YouTube, on the Crack website there, which you could have a look at. So again, we'll just plug some values in. So just a little bit of background on Q in case you haven't seen that video. Q is all to do with the sharpness or steepness of a filter curve, basically. So you've got a curve which relates to an LC circuit, and it could relate to this circuit, or it could relate to a parallel tuned circuit, depending on what you put on the vertical axis, whether it is voltage or impedance. But because we never get pure inductors or pure capacitors, there's always a bit of resistance sneaking around. What we do is we represent it with a resistor as well. Okay, the more the resistor is there, the more the shape tends to be like that instead of like that. Okay, the lower the value of resistance. So resistance acts to damp LC circuits, and it spoils their selectivity. And Q is a measure of how good or how steep the curve is. So there are two ways of doing it here. There's one where we're looking at a one with L in it, and one where we're looking at C in it. So let's have a look just from the point of view of the calculator at the first one. So it says Q is equal to 2 pi FL over R. Now what we can do here is put some values on it. Let's say the frequency is 1 megahertz. Let's say the frequency is 500 kilohertz. That's more, it's closer to an IF frequency of a receiver, maybe. Okay, and let's say that L would be, I don't know, 100 microhenries. And R, we'll say, is equal to 100 ohms. So let's put that into the calculator and see where we get to. So here we're saying here that if the top part of it looks to be the most complicated, so we can work that out first, get an equals to evaluate the total of that multiplication, and then simply divide it by R. So we switch the calculator on, press clear. We can go straight into it. We can say 2 times pi times 500 EE3, that's for frequency in kilohertz, times 100 EE6, change sign, and now we can press equals to evaluate the top part of the equation. So I press equals, and we're there. Now I have to say divided by R, which is 100, equals, and I've got a Q of 3.1415, a Q of about 3. So we'll go through that again. 2 times pi times 500 kilohertz times 100 microhenries equals, divided by 100 equals 3.14, but not to all intents and purposes. I'll put this down there. So there we have it. So it would be a similar calculation for 1 over 2 pi FCR as well. There I would work out the bottom bit, and then I would flip it using the 1 over x button. We've done that a few times, but let's do that then. Let's say we had C being, I'll add it to this one here, C being equal to 20 picofarads. Let's see what it looks like. Okay, so working out the bottom, 2 times pi times 500 EE3, that's kilohertz, times 20 EE12 for picofarads, minus, so that's change sign. Change sign it has, times 100 equals, and then 1 over x to give us our Q there of 159. So moving on to the next of the equations. Now this one here is another way of measuring Q. I don't think this one's too difficult. This would be looking at the bandwidth at the 3 dB points, okay, and evaluating what the Q was by another method. So this is, if you like, knowing the component values or the equivalent values, and this next one is by looking at the curve. So if we look at the curve, whoops, look at the curve, it'll have half power or 3 dB points. And you draw those down to the frequency axis. Whoops, not very good axis here. And there's a center frequency there, which they've marked FC. And then we've got F upper and F lower. And I think on the sheet there, the capital F is a mistake. I think I don't think they meant to do that. So don't read any significance into the fact that it's small fu minus capital Fu. I think that's just a typo on the syllabus there. So if we had 500 kilohertz FC, and let's make this a really good filter, the lower frequency FL at the 3 dB point is 490, and the upper frequency is, to make it symmetrical, 510 kilohertz. What does Q turn out to be? You can see why the upper frequency minus the lower frequency is the bandwidth, because it's that gap there, isn't it? So let's put that into the calculator. The upper frequency is 510 kilohertz. And for this one, to be honest, you don't have to worry about it being in kilohertz, because everything's in kilohertz, and I don't think it would. It doesn't really affect it whether you stay in kilohertz or not. But let's do it in engineering notation. Second function, engineering, 510 kilohertz. Whoops, I'll start again. 510 EE3 minus 490 EE3 equals, and that's 20 kilohertz. That's the bandwidth. Now that's worked out the bottom, so I'm going to divide it by the top and then flip it upside down again as being the easiest way of doing it. Okay, I'm going to say divided by 500 equals, and then the 1/x button flips it over, and I've got 25 times 10 to the minus 3, which doesn't seem reasonable. Perhaps it is though. Yes, I think because it's not a very good, it's not a very high Q circuit. Go through that one again as I'm slightly unsure of it. I'm going to say 510 kilohertz minus 490 kilohertz equals 20 kilohertz. Divide that by 500 kilohertz and then flip it upside down. That's better. I've got 25. So I obviously made a keystroke error on the first one. So there is a Q of 25. Okay. Moving on to the next equation. This is dynamic resistance. RD equals L over CR. So given a C and an R and an L, so L will be in henries, C will be in farads, R in ohms, work out the dynamic resistance. Again, this plays into LC circuits and Q, and is the subject of the video. So have a look at that and work it out. Now this is a fairly easy calculation. I think at this stage, I won't pause on this one. It should be fairly easy. I would enter the figures in using engineering notation, because C will be something like microfarads or picofarads or something. L may well be in millihenries. I would enter in the bottom, divide it by the top, and then flip it using the 1/x key afterwards as being the simple way of doing it. Having said that, I will go through this one and we'll use it as an introduction on how to use brackets. So let's have a look. It says here then, RD, dynamic resistance, is equal to L over CR. Now let's have a look how we might do this one. Let's say that L is going to be 1 millihenry, C is going to be 1 microfarad, and R is going to be 1 kilo ohm. Now let's do it the way that I mentioned before, the way I think is probably the easiest and requires the fewest keystrokes, would be to make sure you're in an engineering mode. 1 EE6 change sign, I'm doing the 1 microfarad first on the bottom, times 1 kilo ohm, 1 EE3 equals. Now I'm going to divide that by the top, which is the wrong way round, but I'm going to say divided by 1 EE3 like that, minus, is equal to 1. So that comes out as 1. Okay, that's the dynamic resistance. So I'll go through that one again. Clear. So we say 1 EE6 change sign times 1 EE3 equals. That's evaluated the bottom. I'm now going to divide that whole bottom by 1 EE3, change sign, and we come up with 1. Let's look and see if I start at the top of the equation. And what I'll be doing is doing this. 1 millihenry divided by, now I need to clump these together. I need to have all of this divided into the 1 millihenry. So I'm going to have to use a bracket here. 1 microfarad times 1 kiloohm to clump it together. Let's see how that works. So I start at the top, 1 millihenry, which would be 1 EE3, change sign, divided by, I'm going to open the bracket, 1 EE6, change sign, times 1 EE3, close brackets, equals, and I've got 1 again. So if you start at the top, you must put brackets around any interim calculation that's on the bottom. Otherwise, you'll get the wrong answer. That times, if you say 1 divided by that and times that times will times the whole thing by 1 kiloohm, not divide the whole thing by 1 kiloohm. And if you're not confused already, here's another way of doing it. I almost hesitate to do it this way, but you can say 1 EE3, change sign, that's 1 millihenry, divided by 1 microfarad, 1 EE6, change sign, and then say equals, and then divide it again by 1 kiloohm. Divide 1 EE3 equals, and you've got 1 again. If you think about what you're doing there, you're saying 1 millihenry is divided by 1 microfarad and then divided again by 1 kiloohm. It's the same as saying 1 millihenry divided by the product of 1 microfarad times 1 kiloohm. Now I hope I haven't muddied the waters too much here. I suppose this just illustrates there are many different ways of doing it and achieving the same result. Brackets are something you should be familiar with because if you have multiplications on the top or something like that and on the bottom, you might find it easier to bracket things up for safety. So let's have a quick look at what I mean by that. Let's say you have 3 times 4 divided by 6 times 8. An easy way of doing that would be to say, to put it into the calculator like this. Because what you've done is you've grouped these together so that the order of calculation is correct. Another way of doing it would simply be to say 3 times 4 is 3 fours are 12, so 3 times 4 equals, and then you have the answer would be 12. I'll write it down there. and you could say divided by 6 equals, and then divided by 8 equals. Again, if you're confused by this one here, just simply ignore it. Just simply use the brackets. So let's move on to another one. That's the end of that row. Right. This one is to do with a Q. This one is just a straight multiplication. We'll be covering that, or it's already covered, I think, in one of the videos. But I don't see any point in going through this one on the calculator, because you're simply multiplying 2 times pi times f times c times rd. And that should be well within your grasp by now. Just stick to engineering notation for your data entry and you'll be fine. Lost my way slightly on this one. Okay, here we have one to do with a transformer. If you recall that in the intermediate course we did look at transformers, and we looked at the turns ratio of a transformer being able to transform the a voltage either up or down, and it became a step up or a step down transformer. So if you had fewer turns on the primary than on the secondary, then it was a step up transformer. You'd have more voltage on the secondary than on the primary, and it would be proportional to the turns ratio, and that's what you see on the equation on the screen there. So let's have a quick look at that one. Let's take a ratio of, let's say, 10 turns to 50 turns. And we can put that in the equation. So this one, the 10 turns, is in the equation you see below, NP, the number of turns on the primary, and this one is the number of turns on the secondary. And if we put in 6 volts here, what will we get coming out? We'll get Vs coming out, because we've got Vp of 6 volts on the primary. So the first thing to do is work out the division part. If you look at that, that's the simplest part. So we simply say 50 divided by 10 equals, that's our turns ratio. I'm going to get out of engineering because I'm not really using engineering units here particularly, so I'm going to go into float. Keep things simple. So our turns ratio is 5. And now I'm going to multiply that by Vp. Vp is 6. I'm going to say times 6 equals, and then we're saying on the on the output, Vs equals 30 volts. Simple as that. Moving on. So we have the same thing here. Actually not quite the same. Of course, it's dealing with the current. The current in the primary is the current in the secondary times the turns ratio. That's the secondary over the primary, the number of turns. If you look back to the previous equation, it was the voltage in the secondary equals the voltage in the primary times the turns ratio. So you can see that we've gone from Vs, voltage in the secondary, and this time the equation is the same, but it's referring to IP. Now, we need to assess, I think, during the course whether or not, and I'll have to look at the syllabus, we need to be able to change the subject of this formula. Because if we look at this formula here, what if you wanted to have IS equals something? You know, you'd need to be able to change the subject of the formula. Now, I'm not sure whether that is within the scope of what is expected of you. And it may not be worth the effort, but let's have a just quick look at it there. We've got IP is equal to IS times NS over NP. If I wanted instead to say IS equals, if I was given the current in the primary and I wanted to work out the current in the secondary, if I wanted to change the subject of the formula to IS, I would need to rearrange this formula a bit. So I'm not sure if you are required to do this. If it's baffling, just put it on hold and we'll look at it in class if it's necessary. Or frankly, I think you can probably, with a bit of luck, get away without having to do it. But let's just do it anyway. So IP is equal to IS, and I'm going to put some brackets around the turns ratio because that's okay. NS over NP. That allows me to think of this as a single term rather than a fraction. So, in the same way as you had, for example, V equals IR, and you divided both sides by R, so you ended up with V over R equals I can do the same thing. I can divide both sides by the turns ratio, making it disappear from this side and appear here. So then I end up with IP divided by NS over NP, which you can work out on the calculator, is equal to IS. Now I can go further than this. I can flip this upside down and bring it up here. You don't have to, because actually at this point you've got IS as a subject of the formula. You could work out this separately and just say IP over the turns ratio equals IS, and that's fine. If you wanted to be a bit more elegant about it, you could write this down as IP NP over NS equals IS. Now, I can't stress enough that this may not be necessary. I think these ones would be a little bit difficult to remember. We'll pay a bit of special attention to these in class, I think, just to make sure that we don't get ourselves all knotted up about them. From the point of view of the calculator, which is what this video is about, it should be fairly simple. The approach should be to work out the turns ratio first, NS over NP, and then simply multiply by IS. Okay. Here's another one to do with transformers. We've talked about transformers stepping up voltage, or being current transformers. They can also be impedance transformers. So what this equation says is that the impedance on a primary is equal to the impedance on the secondary times the turns ratio squared. So what we're saying simply here is that, oops, I've selected the wrong pen. If we've got a transformer like this, perhaps this one is connected to a speaker, the secondary. And perhaps this is connected to, I don't know, some circuitry. And what's happening here is this transformer is matching the circuitry to the speaker. So we'd have a certain impedance here, ZP, and we'd have a certain impedance of the secondary, ZS. That coil would have an impedance. So what we're saying is that the primary impedance is the secondary impedance times the turns ratio squared. Now again, this should be simple enough to do on the calculator. The approach would be to work out the turns ratio. Let's say the turns ratio was 5 to 20. Okay, so the turns ratio, actually it's the inverse of the turns ratio squared. So if we said that the secondary impedance was 8 ohms to match into the speaker, what would be the primary impedance? Well, first of all, whoops, move the calculator. Yeah, first of all, we'd work out NP over NS. So press clear. So NP over NS would be 5 divided by 20. So that's actually the inverse of the turns ratio. And we can square that with the x squared button. And now we can multiply that by 8. And the impedance of the primary then would be 0.5 ohm. Now that's not a very good example because that isn't the sort of value you'd expect to match the transistor output circuitry, but it's just illustrating the use of the calculator there, so you'll have to forgive me that one. Okay, moving on, let's have a look at the next row. Oops. This one here is to do with transistors. All it's saying is that the current in a transistor, now we looked at transistors in the intermediate course, and for those of you that did the intermediate course with me, we did talk about the transistor as a current amplifier. We said that this is a not pointing in transistor, NPN, and here's the base, and here's the collector, and there's the current on the collector, and small changes here make big changes here, and the difference between them is or the gain beta is equal to the collector current divided by the base current. So if you, for example, put in, I don't know, if you get 100 milliamps for 1 milliamp on the base, then your gain is 100 times. That's what beta is there. So beta equals IC over IB. They've rearranged that formula. They've said multiply both sides by IB. So then you've got beta IB is equal to IC. In other words, the collector current is equal to the base current times beta, or beta times the base current. So there you have it. That's the one there. Now, again, I think the skill would be in being able to change the subject of this formula. Something you perhaps need to look at. You get a lot of them with 3 variables. They're all of the sort of V equals IR. You know, if you can do it with V equals IR, you can do it with IC equals beta times IB. It's just something equals something times something. So Using the calculator on this is not particularly difficult. It's simply multiplying or dividing things in the normal way. This one here I think we'll skip. This is to do with synthesizers and stuff like that. Again, this one again, the same thing. We'll skip that until we actually cover those. Nothing particularly difficult in terms of the calculation, in terms of for the calculator. And that brings us on to perhaps the one that gives people the most trouble, ones like this. And I need to make this a bit smaller, don't I? There it is there. Okay, gain or loss equals 10 log 10 power out over power in dBs. Okay, and the one below it is gain or loss is 20 log 10 voltage out over voltage in. So let's have a quick look at this one here. Gain or loss in dBs. In the intermediate course we said that dBs were a logarithmic ratio. Okay, and we said that they always had to be in relation to something. They showed a gain or a loss in relation to something. You had to have a starting value. And the only time you don't, and one is assumed, is where you have an amplifier. And here is the symbol for an amplifier. It has an input and an output, and it could have a gain. And I think in the foundation course and in the intermediate course we learnt some equivalencies between linear gain and dBs. So for example, we said that 0 dB was equal to 1 times, 3 dB was equal to 2 times, 6 dB is 4 times, and I think, well, I know 10 dB is equal to 10 times. Right, now this is fine if we can have a gain or loss that is sums and differences of these. For example, we can combine 6 and 3 to make 4. We can say 6 and 3 is 9 dBs, and that's 4 times 2, which is 8 times. So I can write that one in here. 9 dB is 8 times. So the rule then is that if you are you add and subtract dBs and you multiply and divide linear ratios. And here now the formula you see on your sheet then is working out dBs from linear ratios. So with this amplifier, let's say it's a power amplifier and I have 1 watt in and 11 watts out. Okay, so I've got a gain of 11 times, for it's gone from 1 to 11. If I try and make it up from the ones I know, I'm struggling. The closest I think I can get is 9 and 3, 9 is 12 dB. Okay, so I beg your pardon, 11 times. I'm on the wrong, this just shows how you can be on the wrong one. The closest I can get is 10 times, which is a 10 dB gain. But I want 11 times, and I'm struggling to make up 11 from these linear ratios. So I can use the formula, and I use the formula. I say the gain of this amplifier, I'm going to put a G in here for gain, okay, is equal to 10 log to the base 10, and don't worry about it being to the base 10. If you use the log button here, then that is that's the correct one to use. Okay, because that is the log and anti-log button for base 10. 10 to the power out over power in. P out over P in. Okay, which is equal to 10 to the log 10 log to the base 10, 11 over 1. Now I'm going to have a quick look and see on the calculator how I can work that out. The first thing to do is to pick the difficult part, the 11 over 1 if you like, and work that out. As it's 11 over 1, it's very easy, but I will do it through keystrokes because if there had been, for example, 2 watts in, we'd need to evaluate that first. So we'd say, for example, on and clear, 11 divided by 1 equals, and unsurprisingly, it's 11. Now we need to find out the log of 11. So we press the log button. Okay, and it says 1.04. And now we need to multiply that by 10 times 10 equals. So that's 10.4 dBs. Okay, and I'm going to write that down with a bit more precision, unnecessary precision, because I'm going to go back the other way in a minute. I'm going to say 10.41392 dBs. Now, if I were given 10 dBs, if I had an antenna of 10 dBs, and I wanted to find out what the gain was in a linear way, for example, to work out effective radiated power, I need to find out what the linear gain of 10.4 dBs is. First thing is I type it in, 10.41392. And the reason I'm using the precision there, which is completely unnecessary, is I'm going to get back to 11 times. This is the objective there. So I first of all need to divide it by 10 because that is in dBs and I need to be in bells, not decibels, but bells. So I divide by 10 and I've got 1.041392. And now I use the second function and then the key above the log which says 10 to the x. So second function, 10 to the x, and I've got 10.999, which is essentially 11. So there you can see I've gone from power out over power in to getting how many dBs, and then I've taken the dBs divided by 10 back into bells and used the 10 to the x button to go back into linear. Now this is something that confuses a lot of people and people get a bit stuck with it. It's just a question of practicing it. And another point to note is this only relates to power. I couldn't have written, for example, if this was a voltage amplifier, 1 volt and 10 volt, and used that equation there, 10 log 10, I would have to use the equation below it, the 20 log 10 equation, and we'll be doing some work on that during the course. So there we have it. That's dBs. That's how to find the dB logarithmic ratio if you know the power out over the power in, or if you know the linear gain, because the linear gain is the power out over the power in. Do one more example of that to perhaps let it sink in a bit better. Let's say that I have an antenna with a gain of 6.8 dB, and I have to write with relation to something, dBi, that's with relation to the isotropic radiator. Okay, and I have 9 watts going in, so there's the antenna. I have 9 watts going in. What is my effective radiated power? So, if you recall from the intermediate course, we need to find out the linear gain. We've got the logarithmic gain, so let's take the linear gain. We've got 6.8 dBi. We need to change that into bells. So we divide it by 10, and that gives us 0.68. And now second function, 10 to the x, gives us 4.78 times. So the linear gain then is 4.779 virtually times. And we had 9 watts going in, so if I multiply that by 9, I've got 43 watts ERP. Okay, I think that probably we'll be going back to that one. This one here is to do with SWR. It's the standing wave ratio. We'll be covering that in antennas. Again, nothing too difficult here, except for if you were doing it from here, the V forward plus V reverse over V forward minus V reverse. Probably the best way to enter that, and you can practice a few examples from the book, would be to use brackets, because there's no particular way of doing this that's perhaps any simpler. So I think if you put it in, you would say SWR is equal to, and if you had, I don't know, VF as being 100, VR as being 60, then you would put it in like this: 100 plus 60 over 100 minus 60 in brackets for the calculator. Now, we could easily do that in our head, but let's do it in its you get the calculator to do the whole thing. So we'd start off with a bracket, an opening bracket, 100 plus 60, and I'm going to close the bracket. And you see, as I close the bracket, it evaluates the result straight away. Now I say divide by, open bracket, 100 minus 60. And you see, when I close the bracket, it's evaluated that 100 minus 60 to being 40. So then I must press the equal sign to complete it. So the SWR is 4, or 4 to 1, which isn't terribly good. Maybe okay, depends. Okay, so that's an example, the SWR one, where you would perhaps use a some brackets. Here we have the gain and loss in for voltage. I don't want to go into that. The techniques are exactly the same as for power, but I think the explanation of why it's 20 log would eclipse the point of this video, which is the calculator. This impedance calculation here, I think this one looks quite simple. I don't think we need to delve into that one. Return loss, this is to do with feeders and way of judging how good a feeder is. The strange thing is, this is probably about the only case where a high return loss is a good thing, a high loss is a good thing. It means how much power you're getting back from the antenna, and you know how much loss the reflected power is experiencing, and the higher the loss, the better. Again, this is just manipulating logs within the calculator, no different particularly from the dB example. In fact, it's in dBs anyway. This one here, bandwidth. This is working out, this is Carson's rule, working out the bandwidth of, or approximating, but pretty accurately, the bandwidth of FM. Okay, let's do one of those, I suppose. Let's have a quick look at that. Carson's rule, right. So what we're saying there is that the bandwidth of an FM signal is equal to 2, and they're using the brackets here, aren't they? Audio frequency max plus delta F, and that is the how much you deviate by. So let's take a typical example. That would be 3 kilohertz, I think, is our maximum. We limit our audio to 3 kilohertz. 3 kilohertz is enough for speech to be intelligible. Music sounds tinny, but we're not transmitting music, but without causing too much use of RF bandwidth. Plus, let's say we had a 5 kilohertz deviation then. Okay, so that would be, we can do it in our head, 5, 6, 7, 8 times 2, that would be equal to 16 kilohertz of RF bandwidth. You can see that's quite high. That's one of the functions of FM. It does use a lot of bandwidth. Let's do that on the calculator using the brackets. We can say 2, open bracket, 3 EE3 plus 5 EE3, close brackets, equals. Oh, I've made a mistake. I'll start one again. I should have said 2 times. 2 times, open bracket, 3 EE3 plus 5 EE3, close brackets, equals 16,000. Now, there's a trap that I fell into. Make sure you don't do the same thing. And that is that sorry, I'm just selecting the pen here. That the equation should be written equals 2 times, and that times is there. I forgot to put the times in. I just wrote it as it typed it in as it was written, and that obviously is not the right way of approaching it. So bear that in mind when you're going through them. Right. Let's have a look at the next one. This one here, ERP equals power times gain, linear. We've worked through an example of that. I think you know what that's talking about now. This is an example of expressing the gain with relation to a dipole, and therefore you've got dBd. So what you're saying here is that an isotropic radiator, which is the theoretical base radiator that from which everything is derived, if you like, if you can imagine it as being a point source in a sort of translucent sort of globe, if you like, translucent sphere, and you have your aerial in there instead. You have a half-wave dipole. You will illuminate, if you like, 2 areas on the dipole, because you know the radiation pattern of a dipole is sort of like that, isn't it? There's the dipole, so it's got two lobes. So it would do that. The proportion of that compared with the total area of the sphere is what gives you your gain, because you're getting some focus. Now you can either quote your gain of your antenna in dBi, which is in relation to the isotropic, or dBd, which is in relation to the half-wave dipole, and I think it's 2.17 dB of gain on the dBd anyway, on the dipole anyway. So again, this is just a logarithmic calculation for the calculator, and we don't have to worry about it too much. So that, I hope, has demystified the equations on the sheet. I hope it hasn't been too daunting. Please be assured that we'll be going through all of these in detail, and we'll have plenty of chance to practice them. So stick with your calculator, keep working on that. The more familiar you become with the calculator, the easier things are going to be in terms of the calculation. Make sure you also understand the multiples and submultiples, and 10 to the minus 6 micro, 10 to the 6 mega, etc. They must become second nature, because you need to read off the screen 10 to the minus 3 and know that that's milli without having to spend ages pondering about that. So get used to those, get those on board, get used to using the calculator, make sure you can use the brackets and the functions that we've been using in sections in videos 2 and 3. Don't worry too much about some of the ones, for example x root y, that we covered in some detail in number 1, because it looks as though we don't have to use those. We can if we like, but we don't have to. So that's it. Thank you very much for listening, and the best of luck with your studies.